All right, in this lesson, we are going to be looking at inverses. And inverses, if you remember, are basically where you switch the x and the y. Okay, so in the regular function, the ordered pair would be AB. In the inverse, the ordered pair that fits it would be on BA. Okay, so it's where you switch the x and the y. Um, One way to find if you can even figure out if there is an inverse is to see if a function passes the horizontal line test. In order for an inverse to exist, a function has to pass both the vertical line test and the horizontal line test. And if it passes both of those, then it's said to be one-to-one. And if it's one-to-one, then the inverse will exist. So once again, if a function passes both the vertical and the horizontal line test, it's a one-to-one function, and I can find the inverse of it. The inverse will exist. If it doesn't pass both the vertical and the horizontal line test, it will not be one-to-one, and the inverse will not exist. Okay? So here are some examples to look at to decide whether I can even find the inverse or not. Okay? So in this first example, it does pass the vertical line test, and it might not look like it, but it does pass the horizontal line test too. This line does not go straight across. It gets closer and closer and closer and closer to zero. So this one passes both the vertical and the horizontal line test. So it is one-to-one. And so basically it's asking you, is it a function? It is a function because it passes the vertical line test. It is one-to-one because it passes also the horizontal line test. And so therefore, because it's a function and it's a one-to-one function, the inverse does exist. Okay? This one fails the vertical line test. And so it's not a function. And if it's not a function, it can't be one-to-one. It has to first of all be a function, then be one-to-one for the inverse to exist. This one's not a function, and so it's not one-to-one, and that means the inverse does not exist. Okay, same thing here. This one fails the vertical line test, so it's not a function. And if it's not a function, it can't be one-to-one, and therefore the inverse does not exist. All right, no inverse. Okay. Over here, it passes the vertical line test, so it is a function. However, it fails the horizontal line test, so it's not one-to-one. And because it's not one-to-one, the inverse would not exist for that. Okay? All right. So when we find the inverse, basically what we do is we switch the x and the y and we resolve for y. And we'll kind of do some examples of this in a minute. But here I'm wanting you to find the inverse of this function. Okay? The tricky part to this is for you to figure out the domain and the range. Okay? So here we go. On this original function, okay, this is my original function right here. My domain, I want to think about what I can put in for x values. I cannot put in 1. If x is 1, then the denominator would be 1 minus 1, which is 0, and I can't have 0 in the denominator. So my domain, x can't be 1. If you were to graph this, you would see that for your range, your y value can't be 2. And I should maybe graph this for you so that you can kind of see this. But your y value can't be 2. You can kind of figure that out if you put, if you have a horizontal asymptote in there. If you put big, big, big numbers in for x or really, really, really big negative numbers in for x, you'll see and look at their end behavior, you can see what happens there. That means nothing to you, I know, unless we graph this, which I must have closed my graph. So hang on just a second. I want to graph 2x over x minus 1 here. I'm going to switch this to the colors so that we can see this a little bit better. 2x divided by x minus 1. And I need to do zoom 6 so that my window goes back to normal. And hopefully you can see that you have a horizontal asymptote there at y equals 2. So your y can be any number but 2, okay? However, the key point is here is that it's really, really, really important to pay attention to what your domain and your range is on your original function, okay? So now I want to find the inverse. That's what that little f negative 1 symbol means, is to find the inverse, okay? So my original function, I'm just going to write this. My original function is f of x, or y, equals 2x over x minus 1. My domain is that my x can't be 1, and my range is that my y can't be 2. Okay, now I am going to work on finding the inverse. Okay, when I find the inverse, what I do is I switch my x and my y, and I resolve for y. So what was a y becomes an x, and vice versa. And now I need to resolve for y. Okay, so in order to resolve for y on this problem, I need to get y by itself, which is slightly tricky on this problem. But I'm going to multiply both sides by y minus 1. That will cancel those out. Okay, and then I'm going to distribute this x through so that I have xy minus x equals 2y. Okay, I need to solve for y, so I need to get this to say y equals, which means I need all the y's together. So what I'm going to do next is I'm going to move this 2y to the left side and this x to the right side so that I have xy minus 2y equals x. I will factor a y out of the left side and then divide. Okay, I'm going to go up here because I'm running out of space. When I divide, I'm just going to recopy that so we don't get confused, okay? And now I need to divide, so I will divide by x minus 2. And so my inverse is that. Now, instead of writing y right there, you need to put it in proper notation. So you're going to do the inverse of x is x over x minus 2. And now, here's the tricky part. Way up here, when we started doing the inverse, we switched the x and the y. Well, remember that your domain is your x's and your range is your y's. So when you do your inverse, you have to switch your domain and your range also. So what was your range becomes your domain, and what was your domain becomes your range. Okay? So in this case, my domain would be that x can't be 2, and my range would be that y can't be 1. Okay? And you're going to be asked for that, and so we have to kind of think about that. All right, now we're going to look at how inverses look graphically. Okay, so here is a function right here. You can tell it's a function because it passes the vertical line test. It's also a one-to-one function because it passes the horizontal line test. And so, yes, it's one-to-one because it passes horizontal. So I know that the inverse does exist, okay? If the inverse exists, because it's one-to-one, to be able to graph it, I need to be able to flip it over the line y equals x, basically, okay? Here's the line y equals x, and I wish I had a grid on here, but it doesn't. But this is the line y equals x. I am going to take that blue line and I'm literally going to fold it over my red dotted line. Some people have a really hard time with this. I am going to start with this section right here. Okay, I am going to just do that, and you can see that it kind of looks like an hourglass, and it should look something like that so that it's symmetric. Okay, and then this section down here, if I fold it, would look something like that. So this is about what my inverse would look like, and now I should have done these in different colors, but this is what my inverse would look like. Okay, and you can kind of sketch it here because there's not a grid, which you're sort of going to have to estimate, and I'll show you another way to do this in a minute. Okay, here's what it would look like a little bit more accurately than my sketch, but I would fold it, and then the inverse would look like that. Okay. Here's one where I have it graphed, and we will do the inverse of this also. By the way, this is a function. And you know what? I should have done this. This is a function, okay, because it does pass the vertical line test, but it is not one-to-one. It fails the horizontal line test, so technically the inverse doesn't exist. However, we're going to pretend it does just so that you can see how to graph this, okay? To graph this, again, you're going to fold this over the line y equals x. Okay, that's a little sketchy, but you get the gist. If you have a hard time picturing how to fold it, literally find yourself some key points. So one key point obviously is right here. You can see that it has the coordinate -2, -3. Its inverse will be switched. So its inverse will be -3, -2. So I'm going to plot the point -3, -2, which would go right here. Okay. This point has the coordinate -3.75 and 0. Okay, its inverse will have the x and the y switched. So I'm going to graph the point 0 and -3.75. I'm going to just erase that so it doesn't get so confusing. 0 and -3.75. All right, 0, -3.75 would be something right around there. Okay, again, literally find some key points and flip them, but it should end up looking something like this when you flip it. Okay, and clearly this inverse is not a function because it's not past the inverse doesn't pass the vertical line test, but the original function doesn't pass the horizontal line test, so technically I should have even found the inverse of it, but that's what it would look like if I were to graph the inverse of that. Okay. Okay, and then we want to be able to prove algebraically that these are inverses of each other, and I will just tell you, in order to prove that something is inverses of each other, two functions are inverses of each other, you have to do these two things. You have to find f of g of x, get x for a result. Find g of f of x, and get x for a result. So basically, you're plugging one function into the other and doing it both ways, and you should get x both times. Okay, so here we go. We'll do this one, and we'll do f of g of x first. That means I take g's function and I put it into f's, okay? So I should have the cube root of x minus 2 cubed plus 2. Well, the cube and the cube root, this and that, will undo each other. So I will have x minus 2 plus 2, which is just x, which is what I should get, okay? Now I will test it the other way around, g of f of x. So now I'm going to take f and I'm going to put it in for g. So that means I have the cube root of x cubed plus 2 minus 2, which is the cube root of x cubed. And then, of course, these guys undo each other, and I just get x. So since both f of g of x and g of f of x both equal x, they are inverses of each other. If they did not both equal x, they would not be inverses, okay? These do both equal x, so they are inverses. All right, and we're going to do one more where we have to find the inverse and think about the restrictions, okay? So again, my original function is basically y equals the square root of x plus 3, okay? Important to pay attention to what the domain and the range are on your original function. Okay, I can't take the square root of a negative number, so I know here that my x value better be greater than or equal to -3. When you take the square root, you can never get an answer smaller than 0. So your y will be greater than or equal to 0. If you want to graph that function and look at it on a graph to figure out your domain and your range, you could, but that's how it goes. Okay? Now we're going to work on finding the inverse. When we find the inverse, we want to switch the x and the y. So I have x equals the square root of y plus 3. And then I need to resolve for y. Okay? So in order to resolve for y, I need to square both sides. So I will have x squared equals y plus 3. I will subtract 3. And I have y equals x squared minus 3. Okay, instead of writing it for y, I was working on finding the inverse. So I'm going to label that as f negative 1 of x. Okay, again, when you find the inverse, you switch the x and the y. Your domain and your range need to switch right along with it. So what was your domain becomes your range, and vice versa. Okay, so now your domain will be x is greater than or equal to 0, and your range will be y is greater than or equal to negative 3. Okay, and that's that lesson.